Hello and welcome to my channel again. So today's video is basically the third video of our ongoing series calculating the hydrogen atom corrections using Dirac equation. Now in today's video what we are going to do, we already have derived the Hamiltonians on the previous class or the previous lecture, and now we are going to calculate the explicit energy corrections from those Hamiltonians by taking their expectation values, as we know we do in the quantum mechanics. Now today's video will be on spin orbit term, and I'm planning to do the next video on maybe the relativistic kinetic energy correction term. Now what we have to understand here, that we will first take the magnetic field to be zero, because in the presence of magnetic field we will see the anomalous Zeeman effect or Pasternak effect or weak Zeeman effect like this. So in this case we will assume on the first place that there is no external magnetic field, and in this particular situation we will calculate the LS coupling term or spin orbit term, and the relativistic kinetic energy, and what we have seen in the Darwin term. Okay, Darwin term is a bit tricky because it is not Hermitian. We have to do the while method to make it Hermitian. Okay, so we will do it on the third video probably from today's. So just let's start today's video. Okay, so we will be solving our energy correction for the spin orbit term. So let me just write the Hamiltonian corresponding to the spin orbit term first. The Hamiltonian we already know is basically HLS, that is equals to minus 1 by 2 mc squared. If you're watching this video directly, either I hope you already know these things that I have done before, or I will recommend you to go back to the first video and start watching from them there, because otherwise you won't get the origin of this term, del, or the things I will be telling here. So del v del r, and then finally L dot s. That's what we have seen on the last class. Let's say this is equation number 1. And now what you have to do is, it's basically pretty simple, that we have to take the expectation value of this Hamiltonian and we will get our energy correction term here. So the most important thing that we have to understand here, that is basically what are the complete set of commuting operators. That basically means that which states, or which which quantum numbers we should use to label our states, because we have to know that basically in quantum mechanical hydrogen atom dealings we deal with N, L, M. Okay, so N is basically for the Hamiltonian, L is basically for L square, and ML basically is for LZ. Now here we have a spin term extra. So what are the other terms that we have to add? This is our question. So our complete set of commuting operators in the case of this HLS will be Hamiltonian, obviously, then the L square term, then the S square term, then total angular momentum, and the jth component of the total angular momentum. Okay, all of these are quantum operators, if you want to write it like that. Now the point is, see that Lz and Sz are not individually commuting, but their sum, or to be more precise, tensor sum is a commuting operator. So this is the thing we have to remind in the case of hydrogen atom dealing with respect to Dirac equation, because in the case of taking the expectation values, we always have to mention what are the complete set of commuting operators, so we can label the states properly. Otherwise it won't make any sense. Okay, we have to take the proper states. So it is very important that we know what are the complete set of commuting operators are. Now in the case of hydrogen atom, we already know what are the potential is, that is V of r equal to minus ZE squared 1 by r. Okay, we know this is a typical Coulombic potential we use in the case of hydrogen atom. Now we have to take a simple derivative here. I will take the simple derivative, that is Z squared by r square. Okay, we will put that in side later. So how our Hamiltonian is getting modified, that is HLS, that is equals to the ZE squared minus, obviously this minus, Z squared by 2mc squared L dot S by R cube. Okay, this is our final form of the Hamiltonian that we are getting after doing the derivative. Now the point is, when we take the delta E, okay, so this is delta E LS, this basically means that we are taking the expectation value of HLS, and with respect to which states, this is the most important part. Here we have to write N L L S J, okay, J, and then Mj. You can write a small j here to represent that it is indeed a quantum number, and then L dot S, obviously, by R cube, and then for the sake of orthogonality, we will not write directly n, but we will write the n prime, L prime, S prime, J prime, and Mj prime. Okay. After calculating all of this, if we do this inner product, we will get a Kronecker delta, because all the states in the Hilbert space are orthogonal. Now we will do these things later, and we will assume that n equal to n prime and n equal to n prime here directly without using the Kronecker delta, because that will make the mathematics messy, and we already know that. So we'll keep these messy things out, and we will just write this whole thing as this. Okay, and we'll assume these are done. Now L dot S. Okay, how to find this L dot S? We basically know that L plus S is equals to our total angular momentum J. I'm not sure if it's properly visible or not. So what we can do, we can square on the both side. Okay, after squaring, actually I know this thing will go on the watermark thing, so I think I have to erase this part. Recently the watermark got a little bit bigger, and that made things a little messy. So okay, I would just square both sides, and that will give me L square plus S square plus 2 L dot S. This is the important part. L dot S, that is equal to J squared, and so L dot S is basically half of J square minus L square minus S square. Okay, this is the fun part. We have got L dot S. Fine. Now if we put the L dot S here, okay, now if we put the L dot S here, what we will get here is J square, L square, and S square as the eigenvalue with outside. So we can do that directly here. I have to erase this part. So let me write what we had here is that ZE squared by 2m squared C squared, and with that we already had L dot S as this, so I will write a half. Now we know that for J square we will get J into J plus 1 for this J. Okay, now if we write this as J and J prime, then we will have delta J and J prime, and I'm avoiding this because we already know these things. Okay, minus L into L plus 1 minus S into S plus 1. Okay, with a I will just write h cut squared by 2, and then what we have here is basically the average of 1 by R cube. I hope that till this part everything is clear. Okay, I'm quickly erasing this part. Fine. Now we basically know what will be the 1 by r cube is. Otherwise we can use Feynman-Hellman theorem to find this, but this is not a Feynman-Hellman theorem class, so I will assume that you already know this thing. I mean, everything cannot be done in a single video. If you guys have any problem, you can just comment below and I will do that, obviously. Okay, this part is already done. Now the average of r cubed, 1 by r cube, is basically z cube by L into L plus 1 into L plus half with a naught cube n cube. N is a principal quantum number. Okay, now here is a fun thing. The fun thing is that we want to express all of these things in terms of fine structure constant, because you know that the energy splitting when we measure in terms of fine structure. So we have to remember that alpha, that is the fine structure constant 1 by 137, is basically h cut by a naught mc, or E squared by h cut c. Okay, if you put this substitution directly here, we will finally end up with, you know, z, I mean the z we can already see, and what you have to do is this part, alpha to the power 4 with a mc squared by 4 n cubed, and then the rest will be normal, j into j plus 1 minus s into s plus 1 minus l into l plus 1. S is typically half, but here we will not assume that. L into l plus 1, l plus half. So this is our final expression that we are looking for. The thing we have to our takeaway, the mathematics was easy. Our main takeaway from this entire video is that the correction due to spin orbit term, the I'm not sure, due to the light, I'm not sure if you can see this. This part is for light, right? I will just write here. Our main takeaway from this video is basically that delta ELS is proportional to alpha to the power 4. Okay, the fourth power of alpha, and proportional to 1 by n cube. These are only two takeaways we have to see, and we will see on the further videos that all the other corrections except the hyperfine, okay, will depend on alpha to the power 4. That's why they are on the same region. So on the second video, what we have seen is that the fine structure Hamiltonian is defined by 3 terms, and I've already written that all of these are considered to be the fine structure Hamiltonian. Now you would have asked at that time that why only these 3? Because these 3 have these amplitudes or this dependence common in them. Okay, so I hope you have understood the video, and I will see you in the next one. Thank you.